Hello, this is Yasaman Qasempour. Today, I'm going to present our paper, Single-Shot, Single-Antenna Path Discovery in Terahertz Networks. Driven by increased spectrum availability at 60 GHz, multi-gigabit per second wireless communication is now feasible and has been already standardized in IEEE 822.11ad and AY. Scaling a spectrum access toward the terahertz regime from 0.1 to 1 terahertz can realize the next order of magnitude in data rate due to the availability of even wider spectral band. In fact, 6G is envisioned to feature terahertz frequency networks, enabling applications such as wireless virtual reality and autonomous cars. To overcome the significantly higher attenuation that exists in millimeter wave band and beyond, wireless communications need to be directional. This means to establish a directional link, wireless nodes need to align their beam before any data packets can be exchanged. This is typically done through a training that includes sequential transmission of beacons under different directional settings, while the other end measures the received power with an omnidirectional beam and identifies the best beam configuration. For a fixed client, this procedure needs to happen only once, but for mobile use cases, constant beam training is required to provide seamless connectivity. The problem of directional beam coordination becomes even more challenging in terahertz frequency regime. First, given that terahertz links lack the omni-reception capability available at millimeter wave, the previously mentioned trial and error technique cannot be applied. Further, terahertz beams are inherently more directional with narrow beams of only a few degrees as opposed to tens of degrees in millimeter wave. This significantly increases the number of possible sender-receiver beam combinations and the overhead of exhaustive training. Finally, as beams become narrower, links get more sensitive to blockage and mobility, which demand for faster adaptation techniques. But what if we had near-instantaneous knowledge of physical path, including line of sight and any potential reflected path between the access point and all clients? In that case, nodes can instantly steer their beams toward the line of sight direction without any need for beam training. In blockage incident, for example, they can redirect their beams toward the potential reflectors, and in mobile scenarios, they can effectively realign their beams as they move. But the key question is, how can we get such path information in mobile terahertz networks? In this paper, we present OPERA, a one-shot path discovery with a THz Rainbow. OPERA's goal is to identify high-rate physical path in real time between the access point and all clients. The key idea is to simultaneously transmit distinct signal with unique spectral signatures across different angles such that each physical path gets its own signature. To create such unique signatures, we introduce Leaky-Wave Antenna to the terahertz control plane. Leaky-Wave Antenna is a metal parallel plate waveguide with a narrow slot open in one side. This device is passive, it's small, it's light, and it's very cheap. And because of that, it can easily meet power, size, and weight constraints of handheld devices. Leaky-Wave Antenna allows a traveling wave inside the waveguide to leak its energy out into free space through that open slot. It has this unique property that the angle of leakage or angle of emission from the waveguide is coupled to the frequency of the input signal. This is rooted in the physics of the waveguide and boundary conditions. In fact, boundary condition imposes that on the aperture where free space mode meets guided modes, the wave vector number k of z should be continuous. From this, and after some simplification, we can find angle of emission phi sub f to be related to the sine inverse of a speed of light over 2bf, b being plate separation and f being frequency. This equation suggests that there is a coupling between emission angle and frequency such that higher frequencies would emit at lower angles and vice versa, just like this blue ray that has lower emission angle compared to the green ray. The frequency versus emission angle plot here suggests that the minimum frequency that emits from the waveguide is above 100 GHz. In fact, Leaky-Wave Antenna gives us a promising solution for beam steering in frequencies above 100 GHz because you can easily steer to a different direction by tuning the frequency of input signal. However, we are still left with the problem of where to steer. To solve this problem, our key idea is to transform this property of angle-frequency coupling into a one-shot spatial signature. To do so, we excite the Leaky-Wave Antenna device with a terahertz pulse, or equivalently a broadband signal in the frequency domain. Once the pulse reaches the beginning of the slot, different frequency components decouple and emerge at different angles. This would fill the space with signals that have unique spectral signatures or colors at each direction. That's why we call this pattern a Terahertz Rainbow. Then we develop a model based on the physics of the Leaky-Wave Antenna and terahertz wave propagation that enables the receiver to correlate the spectral properties of measured signals with path directions. So one key question in design of Opera is how to relate the received signal to the properties of underlying physical paths. To answer this, we need to first understand and model the spatial-spectral signatures of wave in a terahertz rainbow. We already know from first principle model that depending on the receiver's location relative to the Leaky-Wave antenna, one particular frequency tone is expected to be received. At lower angles, a higher frequency tone, and vice versa. However, when we measure power spectrum in practice, we found that at any direction, a wide range of frequencies are present with sufficiently high power. In this heat map, I am showing power corresponding to a range of frequencies from 150 GHz to roughly 700 GHz and for a range of angles from 10 to 80 degrees. Putting it in a different way, any specific frequency emits not only at one particular angle, but at a range of angles. Based on this measurement insight, we need to model the spectral behavior as a function of angle. So an input of frequency f would emit out with maximum power at the previously predicted angle of phi sub f, but also spans wider in space with less power. To understand this broader angular width, we treat the leaky waveguide slot as a finite length aperture, which produces a diffraction pattern in the far field. With this, we aim to model the amplitude of signal of frequency f at angle of phi as g of phi and f. After some simplification, we model leaky wave antenna emission for any frequency f as a spatial filter or a directional radiation pattern that has highest directivity along angle of phi sub f. So g of phi sub f and f is 1, but also falls off on both sides with a frequency-dependent rate that we denote as gamma of f. It turned out that there is no close form relationship for gamma of f, but it's solely a function of frequency, and it can be measured and known a priori after production of leaky wave antenna. So all the parameters in this model are fixed and can be known in advance. Our experiments confirm that this model can effectively capture the leaky wave antenna transmission properties, at least for an angular range of interest where the measured power is within the 3 dB of maximum power. In this plot, I'm showing the measurement data and model of G for 4 different frequency values. For larger angular offsets, we can observe irregularities in the measured power that it's not captured by our model. However, the signal strength here would be substantially weaker with this larger angular offset, and thus this would not significantly impact the path discovery performance. While Terahertz Rainbow is composed of signals in all directions within a sector of 90 degrees, only those signals that are along the dominant path of the wireless channel would reach the receiver. Each path contributes to the received signal based on the angular dependent spectral signature, which we modeled as G, and its complex channel gain alpha. With this, we can model the total power spectrum based on the aggregated effect of signals from all paths reshaped by Leaky-Wave Antenna spatial filter, and here P is the total number of multipath components. While this is the modeled power spectrum, we can also measure the actual power spectrum at our broadband detector. In practice, power measurements are available over a discrete set of frequencies depending on the clock sampling rate. We can form an optimization framework to estimate path angles that best describe the power measurements across the entire spectrum. In a nutshell, if we compare Opera against conventional beam training schemes, here are the key differences. In a conventional scheme like beam training in 822.11ad or AY, the access point uses unique beam ID for transmission of beacons in each directional setting, so that the receiver can correlate the power measurements with the transmitter direction through that unique ID. In Opera, we instead use spectral signatures at each angle. Also, to ensure successful decoding of this beam ID, conventional approaches train one beam at a time, whereas here we transmit spectrally different signals at all directions at once. Finally, Opera saves orders of magnitude in training time as it eliminates the need for decoding and it reduces the number of transmissions to 1. We conduct extensive over-the-air experiments to characterize the properties of Terahertz Rainbow and evaluate the performance of Opera. We exploit a custom-built Leaky-Wave Antenna device shown here, which we built using 4x4 cm metal plates and 1 mm spacer in between. For terahertz pulse generation, we use laser-based broadband source that down-converts a femtosecond laser to terahertz frequencies. The generated picosecond long terahertz pulse in time domain and frequency domain are shown here. Our terahertz pulse source is extremely low power with an average power of roughly minus 10 dBm. This is time average power integrating over the entire 1 terahertz of spectral band. Because of this, we are bound to conduct a small-scale experiments having a range of up to a meter or so. Having said that, increasing the transmit power does not affect the properties of Terahertz Rainbow nor the design of Opera. To create different multipath settings, we set an aluminum sheet as a reflector and slide it on a rail to vary the non-line of sight angle while we are trying different line of sight positions. Since Opera identifies different paths through their angular dependent spectral signatures, when we have two paths that are spatially close, meaning they have close angle of departure, then their spectral profiles become similar and that might make them indistinguishable. Hence, one key question here is the minimum required angular separation that is needed so that one can successfully extract signatures from the superposed received signal. To evaluate this experimentally, we fix the line of sight path and slide the reflector along the rail to create different non-line of sight settings. Here in this plot, I'm showing the non-line of sight estimation error in degrees offered by Opera against the angular separation between line of sight and non-line of sight path. We found that at different multipath settings, we are still able to detect the line of sight path reliably because it's substantially stronger. However, when multiple paths are sufficiently angularly separated, meaning the line of sight angle and non-line of sight angle have a distance of more than 3 degrees, then Opera can successfully extract the non-line of sight signature from the superposed signal. In more than 300 multipath configurations that we tested, the average estimation error for line-of-sight path is 1.1 degree, and for the non-line-of-sight path is 1.9 degree with higher variation. Next, we evaluate the performance of Opera for beam adaptation in mobile use cases. Here, we periodically excite the Leaky-Wave antenna with a terahertz pulse to generate the THz Rainbow and let the client keep track of the line-of-sight direction. Having the line-of-sight estimate, then we can instantly adapt the transmit beam as the client moves. However, as I mentioned in the previous slide, Opera provides path directions within 2 degrees of ground truth. This means that our beam steering is suboptimal as we are maximizing our directivity gain along the direction that is slightly off compared to the ground truth line of sight angle. This would cause Opera to experience SNR penalty compared to what an oracle approach with perfect knowledge of path can achieve. Here, I am evaluating the amount of SNR penalty by showing empirical distribution function of SNR loss for Opera compared to an oracle approach with maximum achievable SNR. As shown here, in 90% of measurement instances, the SNR penalty is less than 1.2 dB. To summarize, Opera achieves real-time path discovery and tracking with a single-shot transmission of a terahertz pulse, which is itself in the order of nanoseconds. Opera has a single antenna design because it requires one Leaky-Wave antenna at the terahertz control plane. Our design is also non-coherent as it uses only power measurements at the receiver and not phase information. This would relax the need to keep tight synchronization between the transmitter and receiver and makes the scheme robust to small-scale channel variations. Finally, path discovery in Opera is scalable such that all clients can simultaneously and independently identify their line of sight and reflected path via analyzing their received power spectrum from a single-shot transmission of a pulse. Our experiments demonstrate that Opera is able to provide path estimates within 2 degrees of ground truth for line of sight and reflected path. If you are interested to learn more about Opera, please check out our paper. Thank you.